We begin. Dear Father, we thank you for this day again, Lord. Thank you for these students. Just pray that you'd guide our work today. Help us to glorify you, Lord, in what we do. In your name I pray, Lord Jesus. Amen. All right, so we're hopefully, not doing a silent film at this point on abstract. Sorry to those of you who were... The thing that's really annoying, as I was just telling you guys, is like last lecture, if you could hear the words, it was really good. But basically, we talked through the first half carefully of... Come on, where'd you go? We talked through the first half carefully of I'll eventually find my words. Excuse me. Come on. We defined a character. We found a way to study linear independence of automorphisms because they're naturally connected to the characters built over the group of the units in the field. Then we studied Theorem 9, which I'll write on the board for the sake of discussion. What did Theorem 9 tell us? It told us that if we had a finite group of automorphisms, a subgroup, right? So sigma 1 equal to 1, sigma 2, sigma n. All right, a subgroup. And I guess in here we tend to use this of ought. Certainly last semester I would have written this. Anyway, it's a subgroup of the automorphisms of a field K, all right, with, what was our notation? Kg equal to F, so fixed field F. Then the degree of K, the degree of the extension of K over F is the order of the group. It's equal to n, which is equal to the order of G. So this is what we proved last time. Well, I mean, if you want to be fussy, we did half the proof and then we talked through the latter half, but really the details of the half we did carefully in here. And the part I left out, we also had done very, very similar arguments over the study of characters. So I don't feel bad about leaving that half out. And since none of the rest of you can hear the audio, let's just say that the proof last time was amazing. Sorry. Just unnecessary. But Corollary 10, so let's go on here. Corollary 10, it says, excuse me, let K over F be a finite extension, any finite extension. All right? Then, what's the punchline? The degree of the fixed field of F over K, ought K over F, is what? It's less than or equal to the degree of K over F. With equality, if and only if F is the fixed field. What? Oh, sorry. Yeah, is the fixed field. Is the fixed field of ought K over F. Put another way, K over F is Galois if and only if F is the fixed field of, yeah, okay, that's better. Let me write that. So let's say that again. K over F is Galois if and only if what? F is the fixed field of the automorphisms What's the proof of corollary 10? Well, let's look at it. It's not long. So the proof, we'll let F1, all right, be the fixed field of ought K over F. So in the Conrad's notation, what would that, how could we write that? Using like the K upper G notation, how would I? Right. So K upper ought K over F equal to F1, right? So it's the fixed field of that. So that what? He points out the base field F is extended by F1, right? And of course, all of this is happening inside the universe K, right? So by Theorem 9, we have what? Theorem 9 tells us that the degree of K over F1 is equal to n. What is n? Oh, I'm sorry, I can't say n. I don't even have an n to work with here. It's the degree of what? The degree of the ought K over F, right? Which we're assuming is, how do I know that that's finite? It's a finite extension, so the number of automorphisms of a finite extension is finite, right? I mean, yeah. And then what? And then we just use the usual. So since this, we can look at the degree of K, right, over F, and that's equal to what? K over F1, right, times F1 over F, right? And that's, of course, equal to what? Ought K over F times F1 over F. What's that say? Oh, so if you just look at that for a second, right? Excuse me, guys. So this is equal to that, right? And you can see that this automatically follows from that because we're, what? I mean, this is at least 1. So it could be 2, could be whatever. And if it is whatever, then there's a strict inequality here, right? If F1 is equal to F, we get equality of K over F, right? And the degree of the automorphisms of K over F. K fixing F, rather. Okay, move along here. Corollary 11. What's Corollary 11 tell us? Corollary 11 tells us let G be a finite subgroup, right, of ought K. Right. And again, we'll let F equal to the fixed field of G, right, K upper G. Then every automorphism, right, every automorphism of K fixing F. What's the punchline here? Every automorphism of K fixing F is contained in G. In other words, ought K over F equals to G. What does that say about K over F? What kind of extension is this? It's Galois, right? With what? What's the Galois group? G, right. So do you guys understand the difference between this and corollary 10? Okay, well, corollary 10 is clearly different. It's about bounding the degree of the fixed field, well, bounding the degree of the extension of a field. Bounding the degree of the automorphisms of a field which fix a subfield by the degree of the extension over the subfield, right? And more than that, we get equality if that subfield is actually the fixed field of that automorphism. Well, it's not the full group of automorphisms, right? It's the part of the automorphisms which fix the subfield. So it's kind of a nuanced statement, right? I mean, it's not the kind of thing we looked at in the last class at all, right? I mean, we were not kind of in the weeds with looking at how fields behave there. But this is what does it say? This says if we have a subgroup of the automorphisms and we look at the fixed field, then any automorphism which is, fixing that subfield, it has to appear in that subgroup. All right. What's the proof? All right, proof. He says, by definition, F is fixed by all the elements of G. I'll say by every sigma in G, because it helps me think about automorphisms. So we have, thus, he points out that G is a subgroup of the automorphisms of K over F, right? I mean, by assumption, everything in G is F fixing, right? He says, and the question is whether there are any automorphisms of K fixing F which are not in G, right? Whether this containment is proper. Okay, well, anyway, this tells us that the order of G, right, is less than or equal to the order of odd K over F, right? I mean, well, that's just, if you've got a subgroup of a group of order 10, it has size at most 10, right? Nothing surprising there. He says, by the theorem, we have that the order of G is equal to K over F. By theorem 9, right? By theorem 9, we have that the order of G is equal to the degree of K over F. And by corollary what? My current numbering, corollary 10, I think. We have what? We have that the degree of automorphisms of K over F is equal to what? Well, excuse me, it's less than or equal to what? The degree of K over F, right? But that's equal to, oh, well, duh, look. So they're equal because we have the inequality for the order both ways, yeah? If 3 is less than or equal to 4 and 4 is less than or equal to 3, then 3 is equal to 4, right? Just saying. That's probably a bad example. That's the danger of making false assumptions, right? All right, so that brings us on to corollary. Let me pick up the pace here if it's possible for me. I don't know if it is. Corollary 12. Corollary 12. Ooh, this is a nice one. I like this marker. Corollary 12 says if G1 is not equal to G2, all right, if these are distinct finite subgroups, all right. Hey, where are all the CFAWs this morning? So, finite subgroups of OT K, right, then K G1 is not equal to K G2. So distinct subgroups lead to distinct fixed fields. That's obviously quite important for the kind of correspondence between the lattice of subgroups and the lattice of fields that we were talking about, that we were suspecting. Yeah. What is it, Sam? Just processing. It's a proof. Suppose F1 is the fixed field of G1 and F2 is the fixed field of G2. If F1 equals to F2, then by definition F1 is fixed by G2. But by the previous corollary, any automorphism fixing F1 is contained in G1, hence G2 is a subgroup of G1. Similarly, G1 is a subgroup of G2, so G1 equals to G2, which of course contradicts them being distinct. So the let's see here, the proof basically is, suppose the fixed fields are equal, then use corollary 11, I think, to force the G1 to be a subgroup of G2, and vice versa, which then implies that they're equal, but they're not, because they're assumed to be. So I won't write that down. It's pretty simple, pretty clear, the proof. Okay, so by the corollaries above, we see that taking fixed field for distinct subgroups of OT K gives distinct subfields of K over F, which is Galois. Further, the degrees of the extension are given by the orders of the subgroups. The degree of the extension is given by the order of the subgroups. That's what's kind of neat here, right? By studying the structure of the group, we can look at degrees. I mean, we have all sorts of things about degrees of subgroups in terms of divisibility of orders, right? All that group theory we learned last semester. And we can kind of start to put together subgroup lattices for a given group. And then this is saying that we can extrapolate from that corresponding degrees of extensions over the base field to which this thing corresponds. Here's theorem 13. Theorem 13, I mean, that's where we're going. The extension, all right, the extension K over F is Galois if and only if K is splitting field, splitting field of some separable polynomial, over F. Furthermore, if this is the case, then every irreducible polynomial with coefficients in F, which has a root in K, is separable over F. I'm sorry, just is separable. And has all its roots where? In where? K. So that would make K over F a separable extension. Now we of course we have observed this phenomena and the lack of it in studying, specific examples before, but we actually haven't proved this result yet, right? So. So let's look at that. This is Theorem 13. So he says, first of all, proposition 5 gives that the splitting field of a separable polynomial is Galois. Proof. Prop 5 says splitting field of separable polynomial is Galois. So that's proposition 5 in chapter 14 of Dummett and Foote, of course. Whoa. Well. So what did we even prove? We might not have proved proposition 5 in class in here. That's back on page 562. The proof is basically on page 561. Whoa. Yeah, we did not prove that in detail. Sorry about that, guys. So it's one of those things that involves the study of how roots of polynomials kind of filter up through isomorphisms to extensions, and how they track from one thing to another. I mean, if you have an isomorphism of two fields, then you can look at an extension of both of those fields separately, where you have a 0 for one polynomial, and you see how the 0 transfers over to the isomorphic polynomial over the isomorphic field and the isomorphic extension, and you can kind of track what happens with the zeros under the natural isomorphism. That discussion is what led to proposition 5. But I mean, we talked about that before, but I'm going to go on here. Try not to put my papers out of order. Eee. Just a second here. All right, we're good. Now, I think maybe the converse is interesting here, though, right? If and only if. So this is the proposition 5 is the really this direction, right? What's that? It should be 14 because this is in. It is 14 because this is a sentence in 14, and it doesn't say anything else. So it would, by the rules of Dummett and Foote, refer to this chapter. So, different books have different conventions in terms of that kind of referencing, though. It is true. So I guess we need to look at the forward direction of this proof. So we're suppose the extension is Galois, right? Which means what? So put yourself back in Dummett and Foote land. Forget about the received wisdom from Conrad about the 4 equivalent statements, right? Because we're kind of like climbing our way up that list of things at the moment. So K over F is Galois. What's that mean? Yeah, so let's see here. He says, we now show that if K over F is Galois, then every irreducible polynomial P of x and F of x having a root in K splits completely in K. So remember, we have the earlier work on separable and irreducible where we showed that.
Well, don't we first have to show that K is the splitting field of separable polynomial? Or is that?
Well, let's see here. let's see if, huh.
Like if we show that every irreducible polynomial functions have lawful law,
Yeah.
then it would automatically be this blank filter.
Yeah.
It
Oh.
could be
Huh. Let's see here. So maybe see if we can understand what he says next. He said, I think he's assuming irreducibility of p of x here. He says we now show that if k over f is Galois, then every irreducible polynomial p of x and f of x having a root in k splits completely in k. So I think he's going to assume that you have an irreducible polynomial over f, which has one root in k, and show that it automatically follows that it has all of its roots in k.
But I'm referring to the first sentence where we said that if it's Galois, then it must be the splitting field of a separable polynomial. Have we already shown that, or is that not necessarily not necessary to show the same thing?
Hmm. Well, if we know Keith Conrad's, then we know all of this. There's five pages of proof there I skipped over to get to that. The 4-part equivalence. Yeah. Yeah.
Well, I'm thinking of you list a basis of k over f, and then you choose polynomials that has the root that is one of the bases.
Oh yeah.
So it's like you can take the minimal polynomial of each f of the bases and then multiply them together.
Yeah.
Ah.
You need to do that separately.
Huh. So you're thinking of actually constructing the polynomial from the extension elements. That's an interesting. I'm not sure right off. I'm going to just go on with this for the moment. So he says set G equal to the Galois group of k over f. We can do that because we're assuming what? That k over f is Galois, right? And so this is just notation for what ought. It's just notation for ought k over f in this case, right? And he says let alpha in k be root of p of x, and this p of x is a, I believe it's an irreducible polynomial in f, all right, by assumption. And consider the elements. So he says consider the elements alpha, sigma 2 of alpha, sigma n of alpha in k, right? Where what? We're assuming that the G has 1 and then sigma 2 and then sigma n, kind of the notation we've been going with for the group up to this point. And he says, well, he calls this is equation 14.9. Right here, this is equation 14.9, and he says, let alpha 2, alpha 3, alpha r be distinct elements found in list of equation 14.9, okay? And admittedly, that's not equation 14.9. I called it equation 14.9. It's list 14.9. My bad. But I just have this habit of calling things that are set apart from text with numbers beside them equations, even when they're not. It's a bad habit, admittedly. So n and r don't have to match in principle, right? Certainly, you can look at a distinct list, sublist of that, logically. He says that if tau is in G, then since G is a group, the elements tau, tau sigma 2, tau sigma n are the same as the elements in some other. So it follows that applying tau to G to the elements in 14.9 simply permutes them. So in particular, applying tau to alpha 2, alpha 3, alpha r permutes these elements. And so the polynomial f of x. So his point is, if you you can permute these. You can 14.9 you can hit with any element tau in G, right? But then because tau sigma j has to be sigma k for some k, because the finite group, when you hit it by one of the things in the group, just permutes the list of group elements, it follows that hitting this list with tau just simply permutes these roots, and thus permutes the distinct roots. And that's true for any tau, which means when we write down f of x equals to, x minus alpha, what can you say about this polynomial? What can we say about this polynomial? It has coefficients which are fixed by all the elements of G. And since the elements of G simply permute, the factors, hence the coefficients lie in the fixed field of G, which by corollary 10 is the field F. So the coefficients of f of x lie in the fixed field of G, which by corollary 10, fixed field of G, with equality if f is the fixed field of k over f, right? So the equality case there. So what's that tell us? Oh, that tells us that that implies that f of x is where? Better yet. Yeah. Because f is the fixed field. The coefficients of this lie in the fixed field, which is f in this discussion. Right? But p of x is irreducible and has alpha as a root. Right? P of x is the minimal polynomial for alpha over f. Hence, it divides any polynomial in f having alpha as root. This is proposition 13.9. It follows that p of x divides f of x. And f of x obviously divides p of x and k of x. So by proposition 2 in chapter 14, we have p of x is equal to f of x. So this shows that p of x is separable and has all its roots in k. Right. In fact, they're among all the elements that we listed in 14.9, which proves the last sentence in this theorem. Yeah. To complete the proof, he says, suppose k over f is Galois, let omega 1 through omega n be a basis for k over f, and let pi be the minimal polynomial for omega I. This sounds vaguely familiar to someone's idea. Check this out. So let pi be the minimal polynomial for omega I over f, and then we have just proved that pix is separable, hence all its roots in k, and just make g from multiplying all of the minimal polynomials created for the basis of k over f, basically. He says let it be the remove any multiple factors as necessary, the square-free part of it. Then the splitting field of two polynomials is the same in this field. The splitting field of two polynomials is the same, and this field is k. All its roots lie in k, so k contains the splitting field. But omega 1 through omega n are among the roots, blah, 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 blah. Yeah. Okay, so I'm not going to... Enough. Sorry. As I said, I don't have time to prove everything in here. I should stop trying to prove everything in here, as we, of course, do not have time to prove everything in here. Yeah. But this finally leads us to Dummett and Foote defining the notion of Galois conjugate, right? Let k over f be a Galois extension, alpha an element of k, sigma alpha for sigma in the Galois group of k over f. That's called a conjugate or a Galois conjugate of alpha over f. And if E is a subfield of K containing f, then sigma of E is the conjugate field of E over f. All right. He says the proof of the theorem shows that in a Galois extension k over f, the other roots of the minimal polynomial for f of any element alpha and k are precisely the distinct conjugates of alpha under the Galois group. And he says the second statement of the theorem also shows that k is not Galois over f if we can find even one irreducible polynomial over f having a root in k but not having all of its roots in k. All right. And then finally, at page 574, so sorry, I've glossed over half of the proof, but in my defense, you guys already agreed with Kang that that's how we should do it, and that was the last half proof we glossed over, which was just to take the basis for the extension and build the minimal polynomials with respect to that basis, put them together to form the polynomial, which this takes the splitting as a splitting field. So there's two stages to the proof. The first stage is just suppose you have a polynomial which has a root, prove that it has that property, then build the polynomial explicitly from taking the basis of the extension and removing duplicate factors to make it separable. So it makes sense.
Wait, do we prove that a finite subgroup of automorphism is...
Hey, this is back again. Go on. Oh, okay. Yeah. So on page 574, he has these four characterizations of Galois extensions: splitting fields of separable polynomials. 2, fields where f is precisely the elements fixed by aught k over f. In general, the fixed field might be larger than f. 3, fields with k over f is equal to the degree of aught k over f, which was our original definition in Dummett and Foote. And 4, finite normal separable extensions. These are 4 different ways to look at Galois extensions. And that leads us finally, to the fundamental theorem of Galois theory, which I will finally write down. All right. So it looks like we'll be back to examples next class. Woohoo! All right. So theorem 14. Of section 14 point what? 14.2. It says let k over f be a Galois extension and set G equal to gal k over f, then there is a bijection of the following form. We can go from subfields E of k containing f, which is nicely, it's nice to put a little tower of fields there. And that's interchangeable with subgroups H of G. All right. So for the fields, we have K as the sort of the universe, I like to think of it. So we have K, E is the intermediate field, F is the base field, right? And then over here, what's the lattice of subgroups on the other side? 1 at the top. So we draw the subgroup lattice kind of backwards from what we did last semester, right? It's upside down. And what's this correspondence? So E corresponds to elements of G fixing E, right? And the fixed field let's see here, the fixed field of H corresponds to, H corresponds to the fixed field of H. And these are inverse under these correspondence. Let's see here, do we have any notation that kind of makes this, so this is what really E maps to what? Gal K over E, elements. Gal. Oh, yeah, I'm sorry. So you say it's Gal K over E? Huh. And what's this map here? Yeah, K to the H. And then we have this list of 5 things that are true about this correspondence. It's inclusion reversing, there's a relation between the degrees, K over E is always Galois, all right? And then E is Galois over F. Number 4 gets to be something a little bit more technical. E is Galois over F if and only if H is a normal subgroup of G. And then in this case, the Galois group is isomorphic to the quotient of G by H. But we'll try to get into these more nuanced. I try to state the rest of it carefully next class. I don't think I have enough time to write that down carefully at the moment. But maybe we have just enough time to... No, I guess we don't. Well, I'm sorry, guys. I guess we had to stop here for today. Don't worry. I'll go like a full 30 minutes over someday to make up for it.